Welcome back. In this video, you will learn how to solve integrals using trigonometric substitution. Let's get to it. Alright, so we are going to look at an integration technique that will allow us to solve integrals of radical functions that previously we may not have been able to solve. Specifically, we're going to be looking at integrals that include one of these three forms of a radical function. And so we have the square root of a squared minus u squared, the square root of a squared plus u squared, and the square root of u squared minus a squared. And for each of those three radicals, a is going to be a constant, such as 1, 2, or 3, and so on, and u is a function of x. And so that could be x, x squared, 2x, 3x, and so on. And so if you come across an integral that includes one of these three radical functions or radical expressions, there is a possibility that you won't be able to solve that integral using any other integration technique. And so that is where trigonometric substitution will come into play. And so what we're going to do is we're going to replace u, our function of x, with an appropriate trig function that will then allow us to simplify our radical functions to a trigonometric expression that we then know how to integrate. And choosing that appropriate trig function to set equal to u is going to depend on which of these three forms you see within your integral. And so let's take a look at each of these forms individually and which trig function we are going to substitute in for u in each case. Alright, so first we're going to be looking at integrals that include this radical expression. We have the square root of a squared minus u squared. And when you see this form in an integral, you're going to want to set u equal to a times sine theta. And now notice that the variable for sine is a different variable. U is a function of x, but we're going to be replacing that with a trig function in terms of theta. And so similar to u substitution, where we rewrote our integrals in terms of u in order to integrate, with trig substitution, we are going to be rewriting our integral in terms of theta in order to solve it. Okay, so it's important to remember that we are working with a new variable of theta, and we will not be using sine x. Alright, and so the reason we choose the sine function as our trig function to substitute in for u for this form is because of the Pythagorean identity for sine and cosine. If you remember, cosine squared theta plus sine squared theta is equal to 1, and if we were to solve for cosine theta in that identity, we would first subtract sine squared theta from both sides of the equation. So here we have that, cosine squared theta is equal to 1 minus sine squared theta, and then if we solve for cosine theta by taking the square root of both sides of the equation, we'll get this right here. Cosine theta is equal to the square root of 1 minus sine squared theta. And then if we slightly rewrite this radical expression, we could rewrite 1 to be 1 squared and sine squared theta to be 1 times sine theta squared. Then notice that this radical expression matches what we have up here. We have a squared, a constant squared, minus u squared, where u is a times sine theta. And so down here we have 1 squared, and so 1 would be a, and that means that 1 times sine theta is u, which matches up with a times sine theta. Right, we said that a was equal to 1, and so 1 times sine theta would be u squared. Alright, and so setting u equal to a times sine theta for this form will allow us to rewrite this radical to be cosine theta. We will be able to simplify that radical expression to just be a single trigonometric function that we will then be able to work with within our integral. Okay, and so that's going to be a common theme as we look at the next two forms. The reason we choose a specific trig function to set equal to u in our radical expression is so that we can make use of some trigonometric identity that will allow us to rewrite that radical expression to be a simple trig function. Now next up we have our second form. When you have an integral with the square root of a squared plus u squared, you're not going to set u equal to a times sine theta. Instead, you're going to set u equal to a times tangent theta. And once again, this choice for u, for this radical expression, comes from a trigonometric identity. Specifically in this case, the Pythagorean identity for secant and tangent. And so recall that secant squared theta is equal to 1 plus tangent squared theta. And so if we solve for secant theta by taking the square root of both sides, we have that secant theta is equal to the square root of 1 plus tangent squared theta. And if we rewrite that expression slightly, then secant theta is equal to the square root of 1 squared plus 1 times tangent theta squared. And so this matches up with this expression right here. We have a squared, or a constant squared, and we have 1 squared here, and then plus u, where u is equal to a times tangent theta. And remember, a is 1, and so if we have plus 1 times tangent theta, we have a times tangent theta, and that is squared, just like u is squared. And so by setting u equal to a times tangent theta, we will be able to rewrite this expression with just secant theta in our integral, which will lead to an easier integral to solve. All right, and so if you see this form of a radical function within your integral, where you have a squared plus u squared, or it could also be u squared plus a squared, the order of addition doesn't matter, but if you see this expression, you want to set u equal to a times tangent theta. All right, and then for our final form, if you see an integral with the square root of u squared minus a squared, you want to set u equal to a times secant theta. Now this is different than the first form we looked at, where we had a squared minus u squared, right? The constant came first. This one is u squared minus a squared, and so this is a different form. Now, similar to the last two, the reason we choose secant theta for u is based on a Pythagorean identity for our trig functions. In fact, it's the same trig identity that we looked at for the previous form, except instead of solving for secant theta, we're solving for tangent theta. And so recall that 1 plus tangent squared theta is equal to secant squared theta, and if we subtract 1 from both sides, we have tangent squared theta is equal to secant squared theta minus 1. And then if we take the square root of both sides to solve for tangent theta will be equal to the square root of secant squared theta minus 1, which can be rewritten to be this expression where you have the square root of 1 times secant theta squared minus 1 squared. And this matches up with this radical expression up here, right? We have u squared minus a squared, where u is a times secant theta. And in our expression, we have 1 squared, which matches up with a squared. So 1 is equal to a, which means that u will be 1 times secant theta, which we have right here. All right, and so setting u in this expression equal to a times secant theta will allow us to rewrite that to just be the tangent function, which will lead us to an integral that is easier to solve. All right, so to summarize everything we looked at, the rules for trig substitution are as follows. If you have an integral that includes the square root of a squared minus u squared, then you want to set u equal to a times sine theta. If you see the square root of a squared plus u squared, then you want to set u equal to a times tangent theta. And if you see the square root of u squared minus a squared, then you want to set u equal to a times secant theta. Now I know that the form for sine and secant are very similar, and it can be hard to remember the difference between the two, but note that when you set u equal to sine theta, the constant comes first, right? A squared is a constant, but for secant theta, u comes first, and remember that u represents your function or a variable. And so the way I personally remember the difference between a squared minus u squared and u squared minus a squared and what trig function to use is that if the constant is first, you use sine, and if the variable is first, you use secant. All right, so just remember the phrase constant sine, variable secant. And that should help you remember which form corresponds to which trig function. All right, but enough talk about the rules. Let's finally take a look at an example problem where we will use trigonometric substitution. All right, so here's our first example. We have the integral of the square root of x squared minus 25 divided by x times dx. Now this is an integral that we are going to want to use trig substitution in order to solve. Right, in the numerator, we have this radical expression, the square root of x squared minus 25. And that expression is in the form of the square root of u squared minus a squared, right? X is our function or variable that corresponds to u, and 25 is our constant squared. And so remember, the square root of 25 is 5, and so we could rewrite this to be x squared minus 5 squared, and now maybe you can see how this corresponds to this form. And so what we want to do is identify what trig function we are going to set equal to u, or in this case, x, because we have x squared and u squared, so u will be equal to x. And then we will use that trig function to rewrite this integral entirely in terms of theta. All right, and so let's identify our trig function. In this case, we have the square root of u squared minus a squared, so we know we're either going to use sine or secant, but note that u, or the variable, is first, and so we're going to use secant. Okay, so we're going to let x be equal to a times secant theta. Now in this case, a is going to come from our a squared term, which in this case is 5 squared, and so a is equal to 5, and so we're going to set x equal to 5 times secant theta. Okay, and so now let's replace x in our integral with 5 times secant theta. We will have that this is equal to the integral of the square root of 5 times secant theta squared minus 5 squared, or I'm just going to rewrite that to be 25 now. Now that we know that a is equal to 5, I'm just going to rewrite that as 25. And then that will be divided by x, but we know what x is equal to in terms of theta, and so we can rewrite that x with 5 times secant theta as well. So we'll have 5 times secant theta in the denominator, and that is multiplied by dx. But hold on, our integral is now written in terms of theta, and so we can't integrate with respect to x, we need to integrate with respect to theta. And so we also need to rewrite dx to be d theta, which we can only do by taking the derivative of what we set equal to x. And so what we will do is take the derivative of x with respect to theta, and then solve for dx, and then we will replace dx with that expression. And so if we take the derivative of x with respect to theta, we will have dx d theta is equal to 5 times the derivative of secant theta. Now remember that the derivative of secant is secant times tangent, so we will have secant theta times tangent theta. All right, and so the derivative of what we set x equal to is 5 secant theta times tangent theta. And now if we multiply both sides by d theta, we can solve for dx, and so we'll have that dx is equal to 5 times secant theta times tangent theta times d theta. And now we can replace dx in our integral with that expression, and then our integral will be rewritten entirely in terms of theta, and then we will be able to simplify and solve it. And so if we replace dx with what it's equal to, we will have that this is equal to the integral of the square root of 5 times secant theta squared. And so let's square each of those parts. 5 squared is 25, and secant theta squared is secant squared theta. So we'll have 25 times secant squared theta minus 25 divided by 5 times secant theta. And now let's replace dx with this expression. So we'll multiply by 5 times secant theta times tangent theta d theta. All right, and so now our integral is entirely written in terms of theta. And so now what we want to do is simplify what we have here and then integrate. All right, and so if I clean up my work here, notice that we have 5 times secant theta in the denominator here, but then we're also multiplying by 5 times secant theta, and so they will actually cancel each other out, right? Anything divided by itself is just 1, and so that's going to help simplify our integral. And then also note that we have a common factor of 25 in each of our terms under the square root. And so if we pull that 25 out, this will be equal to the integral of the square root of 25 times secant squared theta minus 1. And that will still be multiplied by tangent theta and d theta. So we have times tangent theta d theta. All right, now by pulling that 25 out of each of these terms, we have now revealed an expression that we can rewrite using one of our Pythagorean identities for trig functions. Secant squared theta minus 1 is equal to tangent squared theta. We looked at this Pythagorean identity when we discussed why we would want to set u equal to the secant function. And so if we rewrite secant squared theta minus 1 to be tangent squared theta, we can further simplify our integral. So this will be equal to the integral of the square root of 25 times tangent squared theta times tangent theta times d theta. Now if I clean up my work again, we can then take the square root of both of these parts. So the square root of 25 is 5, and the square root of tangent squared theta is tangent theta. And so this is equal to the integral of 5 times tangent theta, and then times this tangent theta, and then d theta. So we'll have tangent theta, d theta. Now we have two tangent thetas that if we multiply together, we will get tangent squared theta. And so this will be equal to the integral of 5 times tangent squared theta d theta. All right, and so now we have simplified to a trigonometric integral that we can solve. Now in order to solve this integral, where we have tangent squared theta, we are going to need to use our Pythagorean identity again, that tangent squared theta is equal to secant squared theta minus 1. And so then if we pull this 5 to the outside of the integral, we can rewrite this to be equal to 5 times the integral of secant squared theta minus 1 times d theta. Okay, and then what that allows us to do is integrate each of these terms. And the integral of 1 is just going to be theta, but then the integral of secant squared theta is just tangent theta, right? We know what the integral is for secant squared theta. Since the derivative of tangent is secant squared, then the integral of secant squared is going to be tangent. And so if I clean up my work again, we will have that this is equal to 5 times the integral of secant squared theta, which is tangent theta, minus the integral of 1, which is just theta. And then we will close that, and then don't forget to add plus c. And so then if I distribute 5 through each of these terms, this is equal to 5 times tangent theta minus 5 times theta plus c. And now this is the solution to our integral, but in terms of theta. Remember, our original integral is in terms of x, and so we want our solution to also be in terms of x. And so now what we need to do is reverse our substitution process and convert our answer from being in terms of theta to being in terms of x. And so in order to do that, we need to reference back to what we initially set x equal to. And so in this case, we have that x is equal to 5 times secant theta. We are going to use this equation to determine what tangent theta is equal to in terms of x and what theta is equal to in terms of x. Now let's start with theta. That's going to be easier. All we have to do is solve for theta in this expression. And so if we divide both sides by 5, we will have that x divided by 5 is equal to secant theta. And then in order to solve for theta, we will need to put both sides of the equation into the arc secant function, or the inverse secant function, right? Arc secant of x divided by 5 will be equal to arc secant of secant theta. And an inverse function and the original function cancel each other out. And so arc secant of secant is just equal to theta, right? Whatever is inside the secant function is what will be left over after these two functions cancel each other out. And so what we have is that theta is equal to arc secant of x divided by 5. And so we can replace theta in our answer here, where we have 5 theta, with arc secant of x divided by 5. So that takes care of that part of our solution. But what about tangent theta? Well, if I clean up my work here, what we are going to do is construct a triangle that we can then use with our trig functions. All right, and so you want to draw a triangle, specifically one with a right angle, and then we'll label one of our other angles with theta. And so now remember how our trig functions relate to a triangle at a specific angle theta. In trig, you might learn the principle of SOHCAHTOA, which tells us how the different sides of a triangle relate to the sine, cosine, and tangent functions. The sine function of an angle is equal to the opposite side from that angle divided by the hypotenuse. Cosine of that angle is equal to the adjacent side divided by the hypotenuse. And tangent of that angle is equal to the opposite side divided by the adjacent side. Now in this case we have secant theta, but remember that 1 divided by secant theta is equal to cosine theta, and so cosine theta would just be equal to the reciprocal of x divided by 5, right? If we changed both sides of this equation to be their reciprocals, secant theta would become 1 divided by secant theta, which is cosine theta, and x divided by 5 would become 5 divided by x. And so cosine theta is equal to 5 divided by x. And from SOHCAHTOA, cosine of an angle is equal to the adjacent side divided by the hypotenuse, which means that 5 divided by x is the adjacent side divided by the hypotenuse, which if we go to our triangle, the adjacent side is this side, which means that that measures 5, and the hypotenuse will be x, which will be the long side of the triangle. Now the other side we don't know, but we can figure it out. If we label that with b, then we know from the Pythagorean theorem that the hypotenuse squared is equal to the other two sides squared and added together. So x squared is equal to 5 squared plus b squared. And so if we solve for b, we subtract 5 squared from both sides. And so x squared minus 25, which is 5 squared, is equal to b squared, which means if we take the square root of both sides, we'll have that b is equal to the square root of x squared minus 25. And so that is the measure of that other side of our triangle. And so now what we can do is use this triangle to rewrite tangent theta in our answer, right? Tangent theta will be the opposite side divided by the adjacent side. And so if we look at our angle here, the opposite side b is the square root of x squared minus 25, and that will be divided by the adjacent side, which is 5. Okay, and so if I clean up my work a little bit, we can rewrite this answer to be that it is equal to 5 times tangent theta, which will be the square root of x squared minus 25 divided by 5, right? That is the opposite side of our triangle divided by the adjacent side. And so then we will subtract 5 times theta, which we said is arc secant of x divided by 5. And so I'll plug that in. We have arc secant of x divided by 5 plus c. Now these two 5's will cancel out, and then we'll have our final solution that our integral is equal to the square root of x squared minus 25 minus 5 times arc secant of x divided by 5 plus c. And so that is the solution to this integral using trig substitution. All right, so to summarize the process we just went through in that example, here are the guidelines you can follow when using trig substitution to solve an integral. You want to start by identifying which trig function to substitute in, and that is based on your radical expression, and so you choose between sine theta, tangent theta, and secant theta. You then want to rewrite your integral in terms of theta, and then once you have done that, you want to simplify and then integrate, but your solution will be in terms of theta, and so then you want to substitute back from theta to terms of x by using a reference triangle. All right, and so that's going to be the general process that you go through for every single integral that you will solve using trig substitution. And so let's take a look at another example. All right, so here's our next example. We have the integral of the square root of 3 minus x squared times dx. Now in this case, our radical expression is in the form of the square root of a squared minus u squared, right? We have the constant minus the function of x, a squared minus u squared. All right, so in this case, since we are subtracting a squared and u squared, but the constant a squared comes first, we are going to set u equal to a times sine theta. All right, so in this case, u squared corresponds to x squared, and so we will set x equal to a times sine theta. Now, what is a in this case? Well, a squared corresponds to 3, and 3 is the same as the square root of 3 squared, right? If you square the square root of 3, you just get 3. And so a will be the square root of 3 in this case. All right, so what we'll have is that x is equal to the square root of 3 times sine theta. All right, and so if we use that, we can replace x in our integral with that expression. But remember, we also want to rewrite dx in terms of theta. And so if we take the derivative of x with respect to theta, we will have that dx d theta is equal to the square root of 3 times the derivative of sine theta, which is cosine theta. And then if we solve for dx by multiplying both sides by d theta, we will have that dx is equal to the square root of 3 times cosine theta d theta. All right, and so now we can rewrite this integral in terms of theta. So we'll have that this is equal to the integral of the square root of 3 minus x squared, but now x is the square root of 3 times sine theta. So we will have the square root of 3 times sine theta squared times dx, which is the square root of 3 times cosine theta d theta. So we have times the square root of 3 times cosine theta d theta. All right, now let's simplify a little bit. This will be equal to the integral of the square root of 3 minus the square root of 3 times sine theta squared. So if we square each part, the square root of 3 squared is 3, and sine theta squared is sine squared theta. So we have 3 times sine squared theta. And that's still multiplied by the square root of 3 times cosine theta d theta. All right, now within this square root, we have a common factor of 3 in each term. And so if we pull that out, this is equal to the integral of the square root of 3 times 1 minus sine squared theta times the square root of 3 times cosine theta d theta. And now what we have revealed is an expression that we can replace with a Pythagorean identity for sine and cosine, right? Remember that sine squared theta plus cosine squared theta is equal to 1. And so if you subtract sine squared theta from both sides, you have that cosine squared theta is equal to 1 minus sine squared theta. And so we can replace 1 minus sine squared theta right here with cosine squared theta. And so if I clean up my work here, we will have that this is equal to the integral of the square root of 3 times cosine squared theta times the square root of 3 times cosine theta d theta. All right, and now if we take the square root of each of these parts, the square root of 3 is the square root of 3, and the square root of cosine squared theta will just be cosine theta. And so this is equal to the integral of the square root of 3 times cosine theta times the square root of 3 times cosine theta times d theta. All right, and now we can simplify this by multiplying the square root of 3 by itself, which is just 3, and then cosine theta times cosine theta is cosine squared theta. And so this is equal to the integral of 3 times cosine squared theta d theta. All right, and so now if I clean up my work again, note that we could pull that 3 to the outside. I'm just going to rewrite this. We'll have 3 times the integral of cosine squared theta d theta. And so now this is where your ability to solve trigonometric integrals, which was the topic of the previous lesson, comes into play. Remember that when you have an integral of cosine to an even power, you're going to want to replace that with its half angle identity. And that half angle identity is that cosine squared theta is equal to 1/2 times 1 plus cosine of 2 theta. All right, and so if we replace cosine squared theta with that identity, we will have that this is equal to 3 times the integral of 1/2 times 1 plus cosine of 2 theta d theta. Okay, and now what we can do is pull that 1/2 to the outside, and this will be equal to 3/2 times the integral of 1 plus cosine of 2 theta times d theta. All right, now in order to solve this integral, I think we should split it up into 2 integrals so we can integrate 1 and cosine of 2 theta separately, because cosine of 2 theta is a composite function and is going to require u substitution in order to integrate it. So this will be equal to 3/2 times the integral of 1 d theta plus 3/2 times the integral of cosine of 2 theta d theta. Okay, and now if I clean up my work again, we can integrate each of these integrals separately. Remember that the integral of 1 will just be 1 times the variable of integration, which in this case is theta. So this is equal to 3/2 times theta. And then for this integral, like I said, we're going to want to use u substitution, where we set u equal to that inside function. So we'll have u is equal to 2 theta. And if we take the derivative of u with respect to theta, then du d theta is equal to 2, right? The derivative of a variable to the first power is just equal to its coefficient. So the derivative is 2. And if we multiply both sides by d theta, we will have that du is equal to 2 times d theta. And then whatever du is equal to needs to be found within our integral, but I only see d theta, I don't see a 2, and so if I divide both sides by 2, we'll have that du divided by 2 is equal to d theta, and now we have a term of du that can replace something that we can find in our integral. And so we'll have plus 3/2 times the integral of cosine of u times du divided by 2, right? We replace 2 theta with u and d theta with du divided by 2. Okay, so if I pull that 1/2 to the outside, this is equal to 3/2 times theta plus 3/4 times the integral of cosine u times du. And the integral of cosine is sine. And so this is equal to 3/2 times theta plus 3/4 times sine of u plus c. But then we just need to replace u with what we set it equal to, which is 2 theta. And we'll have that this is equal to 3/2 times theta plus 3/4 times sine of 2 theta plus c. And now we have the answer to our integral in terms of theta, which means that now we are ready for our last step, which is to work our way back into terms of x by manipulating our original substitution. And so if I clean up my work here, we need to determine what theta is and sine of 2 theta. Now theta will not be an issue to find. We can just solve for theta in this equation here. But sine of 2 theta is going to be a little more tricky. If we're going to use our triangle, like we did in the previous example, it's not going to be very straightforward how we evaluate sine at 2 times theta. And so we don't want to work with this double angle. We'd rather work with just theta within a trig function. And so this is where another useful trigonometric identity is going to come into play. And this is one that you want to write down because it's going to appear often when working with trigonometric substitution, especially when you were trying to rewrite your answer in terms of theta back in terms of x. And so what you want to know is that sine of 2 theta is equal to 2 times sine theta times cosine theta. And this is going to allow us to use two trig functions with just theta, not 2 theta, that we can express in terms of x by using the triangle that we will construct. And so we will rewrite this answer to be equal to 3/2 times theta plus 3/4 times 2 times sine theta times cosine theta plus c. All right, so we just replaced sine of 2 theta with 2 times sine times cosine, which is just using another trigonometric identity, specifically a double angle identity. And so if we simplify a little bit again, 3/4 times 2 will be 3/2, and so this is equal to 3/2 times theta plus 3/2 times sine theta times cosine theta plus c. Okay, and so I'll clean up my work again, and then we will work on rewriting our answer in terms of x by using a triangle. All right, now before we draw our triangle, let's figure out what theta is equal to by solving for theta in this equation. If we divide both sides by the square root of 3, we will have that x divided by the square root of 3 is equal to sine theta. And if we put both sides into the arc sine function, or the inverse sine function, we can solve for theta. All right, and so if we do that, we will find that theta is equal to arc sine of x divided by the square root of 3. And so I'm going to rewrite that first here. We will have that this is equal to 3/2 times theta, which is arc sine of x divided by the square root of 3. All right, now for our other term here with sine theta and cosine theta, we are going to need to use our triangle, at least for cosine theta, because we already know that sine theta is x divided by the square root of 3, thanks to our substitution. All right, so we can actually put that in right away. We'll have plus 3/2 times sine theta, which is x divided by the square root of 3. But now we need to draw our triangle to rewrite cosine theta. So here's our triangle. Remember that this is a right angle, and then this will be theta. And so in this case, if we're going to use SOHCAHTOA, remember that sine is opposite over hypotenuse. And so we know that sine theta is equal to x divided by the square root of 3. And so x is the opposite side, and the square root of 3 is the hypotenuse. So if we look at theta, the opposite is x, and the hypotenuse is the square root of 3. Now in this case, the other side will be b, and using the Pythagorean theorem, we know that the hypotenuse squared will be equal to the other two sides squared and added together. So the square root of 3 squared is equal to x squared plus b squared. And so if we solve for b squared, we will subtract x squared from both sides of the equation, and the square root of 3 squared is 3. So we have 3 minus x squared is equal to b squared, which tells us that b is equal to the square root of 3 minus x squared if we take the square root of both sides of that equation. Okay, and now that we know that that is what b is equal to, we can rewrite cosine theta by using this triangle, and we know that cosine is the adjacent side divided by the hypotenuse, and so if we're looking at our angle here, the adjacent side b is the square root of 3 minus x squared, and our hypotenuse is the square root of 3. So we will rewrite cosine theta to be the square root of 3 minus x squared divided by the square root of 3, and then don't forget to add plus c. All right, and so if I clean up my work here, we can simplify our answer. Notice that we have the square root of 3 times the square root of 3 in the denominator here. That will become 3, and that will cancel out with this 3 in the numerator. And so this 3 and these two square roots of 3 will cancel out. And so what we will be left with is that this is equal to 3/2 times arc sine of x divided by the square root of 3 plus 1/2 times x times the square root of 3 minus x squared plus c. Right, since that 3 and these square roots of 3 canceled out, we just have 1/2 and then x times the square root function. And so this is the final solution to this integral using trigonometric substitution. Let's look at one more example for this video. All right, so here's our last example. We have a definite integral from 4 to 4 times the square root of 3 of 1 divided by x squared times the square root of x squared plus 16 times dx. All right, so in this case, the process is going to look a little bit different because we have a definite integral. In fact, you could argue that it's going to be a little bit easier because if you do your work correctly, you actually won't need to change back in terms of x in order to find the solution to the definite integral. All right, but we'll get to that. Let's start by just identifying what trig function we are going to use to substitute in for this integral. Now in this case, we have a square root of x squared plus 16, and that is in the form of the square root of u squared plus a squared. And so whenever you have u squared plus a squared or a squared plus u squared, you know that you should set u, or in this case, x, equal to a times tangent. You want to use the tangent function. And so we will have that x is equal to a times tangent theta. But now in this case, what will a be? Well, a will come from a squared, which corresponds to 16. And so if 16 is a squared, the square root of 16 is 4. And so a is equal to 4. So we will rewrite a to be 4. Okay? And so if we use that substitution, remember that we also need to replace dx. So we need to take the derivative of x with respect to theta. So dx d theta is equal to 4 times the derivative of tangent theta, which is secant squared theta. And then if we solve for dx by multiplying both sides by d theta, we will have that dx is equal to 4 times secant squared theta d theta. All right, and so now let's use what we have here to rewrite our integrand and dx in terms of theta. So we will have that this is equal to the integral. And remember that these bounds of integration are values of x. So I'm going to write x is equal to 4 times the square root of 3, and x is equal to 4 for our bounds. And then if we rewrite the inside of our integral, we'll have 1 divided by x squared, which x is equal to 4 times tangent theta. So we will have 4 times tangent theta squared times the square root of x squared. So we're going to have 4 times tangent theta squared again plus 16, and that will be multiplied by dx, which is 4 times secant squared theta d theta. So we multiply by 4 times secant squared theta d theta. Okay, now if you wanted to, you could solve this definite integral by then simplifying what we have here and integrating in terms of theta, and then getting your answer back in terms of x to evaluate at these bounds of integration. But that's actually a lot more work than you need to do. What we can do instead is convert our bounds of integration from values of x to be values of theta, and so then we eliminate the need to ever convert back in terms of x. And that means that we won't need to use that triangle that we had to construct for the previous two examples. And so we can bypass all of that extra work if we just convert our bounds of integration to be in terms of theta. Either way, you will get the correct answer, but converting your bounds from x to theta is going to save you a lot more time and is ultimately the easier method. Okay, and so in order to convert the bounds, we're going to use our original substitution that x is equal to 4 times tangent theta. We will plug in our values of x into x in that equation and then solve for theta. And so if we do that, we're going to have 4 times the square root of 3 is equal to 4 times tangent theta. That's for our upper bound. And then for the lower bound, we will have 4 is equal to 4 times tangent theta. Now if we solve for theta in this equation first, we'll divide both sides by 4, and that will cancel out with this 4. And so we're just going to have that the square root of 3 is equal to tangent theta. And now if you have a calculator, in order to solve for theta, you can evaluate the arctangent function at the square root of 3, right? So if you use the arctangent function or inverse tangent function on both sides of this equation, that will solve for theta. And if you did that, you would find that theta is equal to pi divided by 3, which makes sense because if you evaluate tangent at pi divided by 3, tangent of pi divided by 3 is the square root of 3, and so theta is pi divided by 3. All right, and then if we work on this equation, if we divide both sides by 4, we will find that 1 is equal to tangent theta. And so if you plug 1 into the arctangent function, that will solve for theta. And arctangent of 1 is equal to pi divided by 4, and so theta is equal to pi divided by 4. And that also makes sense because tangent of pi divided by 4 is equal to 1. All right, and so what we find here is that our upper bound, x equals 4 times the square root of 3, can be replaced with theta is equal to pi divided by 3, and our lower bound, x equals 4, can be replaced with theta is equal to pi divided by 4. And so we can rewrite those bounds, and since the rest of our integral is already written in terms of theta, we don't need to worry about writing theta is equal to those values. We can just write those values as they are. So we will be integrating from pi divided by 4 to pi divided by 3. Okay, and so if I clean up my work here, we can simplify our integral. I'm going to move 4 times secant squared theta to the numerator, and so this will be equal to the integral from pi divided by 4 to pi divided by 3 of 4 times secant squared theta divided by 4 times tangent theta squared. So if we square each part, we'll have 16 times tangent squared theta times the square root of 4 times tangent theta squared. And so we'll have 16 times tangent squared theta again, and then plus 16 times d theta. All right, and so if I clean up my work again, we can pull out a common factor of 16 from each of these terms. And so if I do that, we'll have 16 times tangent squared theta plus 1. And so rather than rewrite the whole integral, I'm just going to rewrite that. We're just going to have 16 times tangent squared theta plus 1 if we pull 16 out of both of those terms. And then what we can do is rewrite tangent squared theta plus 1 using one of our Pythagorean identities. Right, we know that tangent squared theta plus 1 is equal to secant squared theta. And so we can rewrite this expression to be secant squared theta. And so if I do that, I'm just going to rewrite it right here. We will have secant squared theta. And then we can simplify by taking the square root of both of these parts. All right, so the square root of 16 is 4, and the square root of secant squared theta is secant theta. And so I'll rewrite this, and we will be multiplying by 4 times secant theta. Okay, and then notice that these 4's will cancel, right? 4 divided by 4 is 1. And then secant squared theta divided by secant theta will just be secant theta, right? This will cancel out with one of these secant thetas in the numerator. And so now if we rewrite our integral, this will be equal to the integral from pi divided by 4 to pi divided by 3 of secant theta divided by 16 times tangent squared theta, right? That secant theta canceled out with one of those, and so we just have 1 secant theta divided by 16 times tangent squared theta times d theta. All right, and so if we pull that 1/16 out to the front, this is equal to 1/16 times the integral from pi divided by 4 to pi divided by 3 times secant theta divided by tangent squared theta d theta. And so now if I clean up my work here, we now have this trigonometric integral that we need to solve. Now in this case, it's not going to be helpful to rewrite tangent squared theta with our Pythagorean identity. We just have secant squared theta minus 1. And that's not really going to help us simplify anything. And so instead, what we want to try to do is rewrite secant theta and tangent squared theta in terms of sine and cosine, and hopefully that will allow us to see how we can solve this integral. And so remember, secant theta is equal to 1 divided by cosine theta, and tangent theta is equal to sine theta divided by cosine theta, which means that 1 divided by tangent theta would be equal to the reciprocal of this fraction, which is cosine theta divided by sine theta. So now in this case, for this integral, we have secant theta times 1 divided by tangent squared theta. And so we could rewrite this to be 1/16 times the integral from pi divided by 4 to pi divided by 3 of secant theta times 1 divided by tangent squared theta d theta. And secant theta can be rewritten as 1 divided by cosine theta, and 1 divided by tangent squared theta can be rewritten to be cosine squared theta divided by sine squared theta. And so I'll do that. Let's rewrite our integral here. We will have 1 divided by cosine theta times cosine squared theta divided by sine squared theta. All right, and that's still multiplied by d theta. And so now what we can see is that this cosine theta will cancel out with one of the cosine thetas in the numerator, and so that will cancel out with one of those. And now if I clean up my work, we can rewrite our integral to be equal to 1 divided by 16 times the integral from pi divided by 4 to pi divided by 3 of cosine theta to the first power divided by sine squared theta times d theta. And now we have an integral that we can solve by using u substitution, right? If we set u equal to sine theta, the derivative of sine is cosine theta, which is also in our integral, and so u substitution is going to work perfectly here. And so if I clean up my work again, I'm going to let u equal sine theta, which means that the derivative du d theta will be equal to cosine theta, that's the derivative of sine, and then multiplying both sides by d theta will give us that du is equal to cosine theta d theta. And now we can replace sine squared theta with u, and so this will be u squared, and then cosine theta d theta will be replaced with du. And so this will be equal to 1 divided by 16 times the integral from theta is equal to pi divided by 4 to theta is equal to pi divided by 3 of 1 divided by u squared times du. Okay, since we're writing this integral in terms of u, I wanted to make sure that we remember that our bounds are values of theta. But now we rewrote our integral in terms of u, and so now we can integrate it, get back in terms of theta, and then evaluate at our bounds of integration. So now 1 divided by u squared is the same as u to the negative second power, right? If we move that to the numerator, the exponent will become negative. And then if we integrate that using the power rule of integration, we'll add 1 to the exponent and then divide by that new exponent. So this is equal to 1/16 times u to the negative first power divided by negative 1, evaluated from theta is equal to pi divided by 4 to theta is equal to pi divided by 3. Now if I clean up my work, we can rewrite u to the negative first power to just be 1 divided by u if we move that to the denominator so that that exponent is positive. And then we can pull this negative out front. And so this will be equal to negative 1/16 times 1 divided by u evaluated from theta is equal to pi divided by 4 to theta is equal to pi divided by 3. And now what we can do is replace u with what we set it equal to, which is sine theta. And so if I do that, we will have 1 divided by sine theta. And now we can evaluate this expression at our bounds of integration. And so if I clean up my work one more time, we will have that this is equal to negative 1/16 times this expression evaluated at pi divided by 3 minus the evaluation at pi divided by 4. So we have 1 divided by sine of pi divided by 3 minus 1 divided by sine of pi divided by 4. Okay, now sine of pi divided by 3 is the square root of 3 divided by 2. So this is equal to negative 1/16 times 1 divided by the square root of 3 divided by 2 minus 1 divided by sine of pi divided by 4. And sine of pi divided by 4 is the square root of 2 divided by 2. And so we have 1 divided by the square root of 2 divided by 2. And then if we multiply negative 1/16 by each of these terms, then we will have that this is equal to negative 1 divided by 16 times the square root of 3 divided by 2 plus, because we have two negatives multiplied together, so it becomes positive, 1 divided by 16 times the square root of 2 divided by 2. And then 16 divided by 2 is 8, and so that's going to happen over here as well. So this is equal to negative 1 divided by 8 times the square root of 3 plus 1 divided by 8 times the square root of 2. Now you could leave your answer like this, or you could decide to rationalize it, but in the end, we just want to know what the actual value is for this integral. And so if you were to plug both of these values into your calculator, you would find that this integral is approximately equal to 0.01621956 and some more decimals. And so that is the solution to this definite integral by using trigonometric substitution. Since we changed our bounds of integration to be values of theta instead of values of x, we were able to evaluate our integral at those values of theta, and so we never needed to rewrite our integral back in terms of x. We were able to entirely skip that step where we would use a triangle. Okay, and so with that is all I had for this lesson. If you want to see some more example problems of trigonometric substitution, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.